Okay, let us continue the third part of today's class. Okay, back to the slides, and please turn to page 141. Okay, CSIR plus CSIT case. Okay, since SIMO systems only have one transmit antenna, okay, of course, because this means single input, there is nothing the transmitter can do to exploit its knowledge of the channel. Okay. Therefore, the SIMO capacity when both CSIR and CSIT exist, C-SIMO CSITR is the same as it is under CSIR alone. Okay, we denote this as follows. Sorry again. C-SIMO CSITR is equal to C-SIMO CSIR. Okay, again, the place of the equation number is not correct. Let me fix it. Okay, good. Okay, next let us see. Wait for me. Okay, let us see section 3.8.2 MISO capacity. Okay, first we also consider the CSIR only case. Okay, in the case of MISO systems, H is 1 by NT. Okay, because for MISO systems, okay, the SO means the single output. So this means that the number of the receive antenna NR is equal to 1. Okay, please do not forget that H is an NR by NT matrix, not NT by NR matrix. So the square of the Frobenius norm of H is equal to lambda. Okay, let me. Okay, well, please wait me. Okay. So why the square of the Frobenius norm of H is equal to lambda? Okay, let us continue. The same as for the SIMO configuration. Okay, let us go back to the SIMO configuration. Okay, because in general, the square of the Frobenius norm of H is equal to summation I is equal to 1 to R. Okay, lambda I. Okay, where R is the channel rank, lambda I is the ith largest eigenvalue of H times H Hermitian. Okay, so then under the SIMO assumption, we can know that there is only one eigenvalue of H times H Hermitian, okay, which is lambda. Okay, so we can know that the square of the Frobenius norm of H is equal to lambda. Okay, so similarly, okay, for the in the case of MISO systems, the square of the Frobenius norm of H is also equal to lambda. Okay, because the square of the Frobenius norm of H is equal to NT times NR. Okay, it follows that for a MISO system, the square of the Frobenius norm of H is equal to NT. Okay, because for a MISO system, the number of receive antenna NR is equal to 1. So we can cancel the term NR here, and only the term NT remains. Okay, combining this with equation 3.11 yields. Okay, let us go back to equation 3.11. Okay, in equation 3.11, okay, we can see that the capacity is equal to this. Oh, sorry. Okay, equal to this equation. Okay, so let me write it on the blackboard. Okay, so let me close it first. Okay, so this is equation 3.17 versus equation 3.44. Okay, and save it in the blackboard of Mimo. Okay, good. Eh? What's happened? Okay, don't forget. Please forget. Okay, so again, because I do not have a blackboard, let me use the sorry, no Chinese here. Let me use the Microsoft Word instead. Okay, so the capacity, okay, is equal to this equation. Okay, this is equation 3.11. Okay, this equation. Okay, next let us go back to the slides. Okay, and turn to page maybe 140. Oh no. Okay. So combining this with what is this? Okay, this means that the Frobenius norm, the square of the Frobenius norm of H is equal to NT. Okay, let us write it here. Okay, and on the same page, we know that the square of the Frobenius norm of H is equal to lambda. Okay, excuse me. Okay, so now we can see that the lambda is equal to NT. Okay, and because now we are consider the meso system, okay, it can be proved that the rank of H is equal to 1. Okay, so R is equal to 1. Okay, because R is equal to 1, there is only one term in this summation. Okay, so we can delete the summation here. Okay, let me delete the summation here. Okay, so now capacity is equal to this equation. Okay, and again, because there is only one eigenvalue of H times H Hermitian, you can prove it. Okay, so lambda I, we can drop the subscript I. Okay, and the remaining term is lambda. Okay, and because the NT is equal to the square of the Frobenius norm of H, and the lambda is equal to the Frobenius norm of H also. Okay, so we can know that okay, excuse me. Okay, so we can know that NT is equal to lambda. where is the lambda? Okay, nt is equal to lambda. Okay, so in this equation, lambda and nt can be cancelled. Okay, cancelled lambda and nt. Okay, so this term can be replaced by rho. Okay, so the capacity is equal to log 2 of 1 plus rho. Okay, let us go back to the slides. Okay, so combining this with equation 3.11 yields okay, C-methyl CSIR is equal to log 2 of 1 plus rho. Okay, let me fix the location. Okay, let me correct the location of the equation number. Okay, good. Okay, which is the same as the expression for a Sisal system. Okay, why are the capacity of methyl and Sisal systems the same under the CSIR only assumption? Okay, I believe that you may also feel that it is very strange. Okay. So let us see. The short answer is that having multiple transmit antennas only provides a capacity benefit if the transmitter has knowledge of the channel and can use that knowledge to adjust its transmission strategy. Okay, however, okay, we only know only the receiver know the CSIR now. Okay, so the transmitter okay do not know the channel matrix H. Okay, so it can do anything, but can only use the equal power allocation. Okay, if the transmitter had knowledge of the channel, it would weight the signals it applies to each of its antennas to create a physical beam that pointed in the direction of the receiver. Okay, it is the so-called beam forming technique. Okay, and we can use the water filling algorithm introduced earlier to find the weight. Okay, that is Pi. Do you remember? P1, P2, P3, etc. That is the power of the ith eigenmode. Okay, creating such a beam would increase the signal to noise ratio at the receiver. Okay, because you make the beam align with the receiver. Okay. So after this alignment, the receiver will has the maximum SNR, okay, and allow the transmitter to increase its data rate. Okay, because the data rate, the upper bound of the data rate is capacity is equal to log 2 of 1 plus SNR. Okay. So now the SNR is increased, so the data rate also increase. Okay, another way of answering the question is to say that with CSIR only, a methyl system cannot have array gain. Okay, what is array gain? Let us see the handout. Okay, page 147. Problem 1. What is array gain? Okay, solution. In MIMO communication systems, array gain means a power gain of transmitted signals that is achieved by using multiple antennas at transmitter and or receiver with respect to single input, single output case. This means that you can use multiple antennas only at transmitter or only at the receiver or both at the transmitter and receiver. Okay, so this is the definition of array gain. Okay, let us continue. Which is needed to increase the throughput over a SISO system. Okay, do you remember which is the what is the throughput? Okay, it is the transmission rate of the message, okay, which is successfully received by the receiver. Okay, it is the throughput. Okay, so throughput is similar to the data rate. However, it only accounts for the correct correct reception. Okay, so throughput is related to data rate, and the upper bound of the data rate is capacity. Okay, so when you has the array gain, you can has a power gain on the received signal. Okay, and the capacity is equal to log 2 of 1 plus SNR. Okay, so when SNR is increased, the throughput also increased over a SISO system. Okay, without such knowledge, the capacity is no better than a SISO system. Okay, what knowledge? Okay, the knowledge means the channel state information at the transmitter. Okay, it should be emphasized that although this result says the capacities of MISO and SISO systems are the same when only CSIR exists, this statement should not be interpreted as saying that there is no benefit whatever to having multiple transmit antennas with CSIR. Oh, can you see the difference between lines, the meaning of lines 1, 2, 3 and the lines 4 to 6? Okay, can you distinguish between them? Okay, what is the difference? Okay, if you do not know the difference, let us see the next page. Okay, as we discussed in chapter 1, and as we will discuss in more detail in later chapters, a MISO system with only CSIR can employ space-time coding to achieve transmit spatial diversity. Okay, let us see chapter 1. Okay, chapter 1. Slides chapter 1, and please open it. Oh, sorry. Okay, please open it and search for the space time coding. Okay. Okay, so this is the first time that space-time coding appears on page 14. Okay, next. Okay, good. In table 1.1, okay, we can see that there are two MIMO techniques. The first one is the spatial diversity, and the second one is the spatial multiplexing. Okay. For spatial diversity, Okay, sorry. The method is to use the space-time coding. Okay, that is. Okay, so let us search for the next. Okay, page 20. Okay, there are many space-time coding. Okay, so if you want to know more, please review the slides of chapter 1. Okay, let us go back to slides of chapter 3. Okay. Okay, which reduces the effect of fading and allows the transmitter to transmit higher data rates. Okay, because we know that the spatial diversity is too compact with the fading, multipass fading. Okay, and allows the transmitter to transmit higher data rates. Okay, because you can reduce the effect of fading, so the system performance will become better. Okay, with the same probability of bit error, okay, then would be possible with a SISO system operating at the same average signal to noise ratio using the same modulation and coding scheme as the MISO system. Okay, you should have an important concept. When you want to compare the performance of two different communication systems, okay, for example, here we want to compare the performance of a MISO system with CSIR only and a SISO system. Okay, you need to make every condition be the same. So we can see that the probability of bit error, or that is BER, is the same. Okay, and average SNR is the same, and the modulation is the same, and the coding, here coding means the channel coding or error correction codes. Okay, and the coding should be the same. Okay. Okay, this is a practical benefit. Okay, however, our statement about the capacities being the same means that, in principle, the maximum error-free data rates. Okay, the maximum error-free data rates means the capacity, okay, of the two systems are the same. Okay, so in theory, the capacity of the two systems are the same. However, in practical, we can have some advantage, okay, by using the space-time coding, okay, on a MISO system with CSIR only. Okay, this distinction, while perhaps subtle, okay, please notice how to read this word. This word should be read as subtle, not subtle. Okay, do not pronounce B here. Okay, subtle. Okay, then what is the meaning of subtle? Okay, let us look at the handout. Okay, page 150. Problem 1. What is subtle? Okay, solution: not loud, bright, noticeable, or obvious in any way. Okay, subtle. Okay, let us go back to the slides. Okay, should be kept in mind. Okay, please let me explain the word subtle in Chinese. It means 难以察觉的 或者是微妙的。Okay. So next, let us see the case. Okay, it is 25 minutes. See you next time. Good.